Welcome to our 7th webinar. This webinar is going to be focused on the CPT for evaluation of soil liquefaction, and it is just part 1 of a multi-part series on liquefaction because it's such a large topic. We will try to answer your questions if you would like to type them in using the question feature in this webinar software. I will try to answer those. I'll write them down, and Dr. Robertson can answer most of them at the end, depending on how many we do get on this topic. So I guess without further ado, I'm going to hand this over to Peter Robertson, and he'll be starting the webinar. Thank you.
Thank you, Kelly. Well, welcome everybody to our 7th webinar. And the next few, so we're probably going to do 3, are related to soil liquefaction. It is a somewhat complicated topic, and so it does require more than just one seminar to cover it. So just to remind ourselves that everything I'm going to say is contained in the CPT guide, and as we've mentioned before, you can download a free copy from a variety of websites, either the Greg website or my own, or from the software website GeologisMickey. It's in the back of the guide under liquefaction. So let's get started, and it's best when we talk about soil liquefaction just to remind ourselves that we do understand what this phenomena is. And essentially it's a loss of strength and or stiffness due to undrained loading. And of course it's a big factor in earthquakes due to the cyclic loading that earthquakes impose on the ground. And the feature you see is sand boils, ground cracking, slumping of embankments, lateral spreading, ground oscillations, and generally in big earthquakes, extensive damage. But there's also another form of liquefaction that can cause flow slides, and they can be statically triggered. Now, they can also be dynamically triggered, one of which can be earthquake loadings, but they can be statically triggered. Now, we're not going to cover that topic today. That will be in part 2. And that's what I often refer to as flow liquefaction or static liquefaction. So our focus today is going to be on liquefaction induced by earthquakes. And that's often referred to as seismic liquefaction or cyclic liquefaction. You've got to have cyclic loading to induce this form of liquefaction. And the key element to it is that if you have a loose saturated sand and you cyclically load it, you can develop pore pressures, and those pore pressures can build up during the cyclic loading, and then eventually you can actually reach a condition of zero effective stress during the cyclic loading. And that's what we're going to talk about today, and as you can see, you can have extensive damage. Now, the other definition is flow or static liquefaction, and this is when you have a strain softening response in the ground. It's not restricted only to loose sands. It can also be sensitive clays or very loose, unstable silts. So you have a strain softening response, and we're going to cover that in part 2. So we're going to talk about cyclic or seismic liquefaction today, and as I said earlier, it's basically revolves around the condition of zero effective stress due to undrained cyclic loading. And so this occurs when you have shear stress reversal. So it's very common in earthquakes in level or gently sloping ground, where the earthquake, the rock motion is where the ground cycles back and forwards, and that induces shear stresses in the ground. Essentially simple shear-induced deformations, and they're cyclic in nature, and they're reversals, so they reverse back and forwards. Now, studies have shown that in very large earthquakes, shear stress reversal pretty well occurs everywhere. Although on steep slopes near the face of the slope, there may not be shear stress reversal. But in large earthquakes, even on fairly steeply sloping ground, you do get shear stress reversal. And so seismic liquefaction is a big issue when you're designing for large earthquakes. And the deformations that result from it are controlled by the size and duration of the cyclic loading. So of course, the bigger the earthquake is, the bigger the shear stresses are. And often the larger the magnitude earthquake, the longer it lasts, and so the more cycles of loading that you have. So it's both the size and duration of loading. So that's what makes it a little bit complicated to actually analyze. And of course, large deformations are possible, as illustrated in these photographs, the upper one from Kobe and the lower one from Moss Landing in California. So the lab evidence of cyclic liquefaction, up on the left hand here is the stress path. So you see an element of soil, and as you cyclically load it, shear stresses are applied, you develop a little bit of pore pressure, and so the effective stress drops, and then as you unload it, more pore pressure builds, and so pore pressures gradually build, and the effective stress path moves to the left and eventually hits the strength envelope, and then when you unload, it essentially moves to zero effective stress, and then it cycles through zero effective stress. It goes up and down the strength envelope, so it is dilating up the strength envelope, but then on unloading comes back to zero effective stress. So if you look at the stress strain curves, initially the stress strain curves are very stiff because the effective stress is quite high, and then as the pore pressures build, the loops of the stress strain curve get progressively flatter due to the decreasing effective stress, and then during unloading it hits zero effective stress, and then essentially the soil has zero stiffness because it's at zero effective stress, and so you get very large deformation, and then it dilates up the strength envelopes and then unloads, has zero effective stress and zero stiffness again. So you get these banana shaped stress strain curves that result in very large deformations. And so if you look at the plot at the bottom, if you look at the buildup of strain against number of cycles, initially there's rather moderate buildup in strain, and then suddenly when you reach zero effective stress you get very large deformations. So that's the lab evidence, and that's supported by model studies, both 1G and the centrifuge, and of course in field observations. Back in the 60s, there were two large earthquakes, one in Alaska and one in Niigata, Japan. And resulting from that, Professor Seed and a number of his students, but primarily Seed and Idris back in the early 70s, they developed a simplified procedure of how to evaluate liquefaction under seismic loading. And it composed of two parts, evaluating the seismic demand and the resistance to cyclic loading. And for seismic demand, they came up with this term cyclic stress ratio. And so they came up with a simplified form of how to estimate the cyclic stress ratio induced by the earthquake. And you can see it's a function of the maximum surface acceleration normalized by gravity, so A max over G. And they took 0.65 of that maximum value. And then it's a function of the total to vertical effective stress, and then right at the end there's a stress reduction factor, recognizing that as you go deeper, this cyclic stress ratio tends to decrease as you go deeper into the ground. And then they link that to the resistance to cyclic loading, and they termed that the cyclic resistance ratio, CRR. And initially they looked at samples. They tried to get undisturbed samples and found that that was quite difficult. Loose sands tend to densify when you sample them, and dense sands tend to get looser when you sample them. So they found that sampling was very difficult in sands. And so that led them to try and develop a relationship based on in situ testing and primarily penetration tests. And initially, of course, it was the standard penetration test looking at the SPT N value. And then, about 30 years ago, with the growing use of the CPT and recognizing the benefits of the CPT, methods started to be developed based on CPT. And in fact, that's what my graduate research was on. And increasingly, we find more people wanted to use the CPT because of its more reliable measurements and continuous nature, etc. And so Professor Seed passed away in the mid-90s, and then following the loss of Professor Harry Seed, NCER organized a workshop to try and bring together experts to develop a consensus on how this simplified method should be updated. And so that was published in a paper in ASC in 2001, often referred to as the NCER method, and the publication had, I think, 20 authors, co-authors, and the lead author was Professor Les Yaud, so it's often referred to as Yaud et al., and we'll talk about that method today, at least the CPT-based method. So when evaluating liquefaction, it's seismic liquefaction is primarily for level ground sites. And the definition of level ground is level ground or gently sloping ground, or level ground or gently sloping ground with a nearby steep slope or free face. So for example, if you have level ground near a river or a lake or a harbor or the ocean where the slope drops away quite rapidly, and so that induces shear stresses in the ground. Even though the ground is predominantly level, there are some shear stresses. And so during an earthquake, those shear stresses can induce lateral displacement, and we'll talk about that later. So the sequence to evaluate cyclic liquefaction is first to evaluate whether or not the soils are susceptible to liquefaction, whether or not they're susceptible to reaching a condition of zero effective stress or close to zero effective stress. You'll see that later. And then secondly, evaluate whether or not the earthquake is large enough to trigger cyclic liquefaction, and if it is triggered, then to evaluate post-earthquake deformations. And we'll talk about both vertical settlement deformations as well as horizontal lateral deformations. So recently the term sand-like and clay-like has become more popular in its use, and in general terms, sand-like soils are coarse or fine-grained soils that are essentially non-plastic and behave very similar to sands. So of course sands are coarse-grained, but you can have silts that are fine-grained, but if they're essentially non-plastic, then they will behave very similar to sands, and the cyclic resistance is usually evaluated within a framework based on in-situ tests, and of course today we're going to talk about CPTs. But clay-like soils, so clays and plastic silts that are more easily sampled, they're less affected by sampling disturbance, particularly clays, and they exhibit a stress history normalized strength parameter properties. And then the cyclic resistance can be estimated based on either in-situ tests, laboratory testing, or empirical correlations based on undrained shear strength. And you'll see that when we talk about cyclic softening of clay-like soils, we will in fact use the CPT and we'll estimate the undrained shear strength, and then through that estimate the cyclic resistance ratio for softening. So to evaluate the susceptibility of soils to liquefaction, so sand-like behavior generally regarded as non-plastic soils or soils with a plasticity index that's quite low. Now it's quite controversial how low. It seems to vary from anywhere from about 7 through to 17 or 18. And on average, a number of 10 or 12 is commonly used. I'll show you the chart in a moment. And then likewise, soils with relatively low liquid limit, and also soils where the water content is large relative to its liquid limit. And we know that whenever soils, particularly fine-grained soils, if they have a water content that's close to the liquid limit, then they tend to be sensitive, and the higher the water content is relative to the liquid limit, then the more sensitive they're likely to be, and therefore the more likely they are to generate large excess pore pressures during both static and cyclic loading. So clay-like behavior tend to be the reverse. These are soils where plasticity index is greater than about 12. Now they don't suffer cyclic liquefaction where it's defined as reaching a condition of zero effective stress, but they can soften. They will develop some pore pressure, and because they develop some pore pressure, the effective stresses do drop somewhat, and so they do deform, but they do not get these banana-shaped stress-strain curves. Their stress-strain curves tend to be more oval. They don't reach zero effective stress, therefore they don't reach zero stiffness during cyclic loading, so therefore they don't deform as much, but they do deform somewhat. And obviously the amount of deformation is linked loosely to how plastic those soils are and how strong they are. So the above criteria are based primarily on classification tests that are actually carried out on disturbed samples. So you don't need undisturbed samples to evaluate whether or not a soil is likely to be more sand-like or more clay-like. And it's controlled primarily by plasticity, although really that's a proxy for the amount and type of clay minerals. The more plastic clay minerals are and the larger the amount of plastic clay minerals, then the more ductile the material is likely to be, and therefore the less likely it's going to reach zero effective stress, and therefore the less it's likely to soften. So, but there is a transition from sand-like to clay-like. Although we've defined it as being roughly a PI of 10, there really is a transition, and as we say, it can vary from as low as 5, 6, or 7, up to as high as 20. And people have often commented that when you try and actually determine a plasticity index less than 10, it's not very accurate. You know, if you remember, the test to determine plasticity index is somewhat crude, so the reliability on this this criteria is somewhat subjective. So there are a number of curves that have captured this. Professor Rayseed and his students in 2003 suggested a relationship that was plasticity index against liquid limit. It's essentially the classic Atterberg limit chart. And if the data falls within the lower left region where the PI is less than 12 and the liquid limit is less than 37, then it's potentially susceptible to cyclic liquefaction. And then there's a region a little bit larger where it may be, and that's a good region to maybe take samples and evaluate how susceptible it is. And then soils outside that are not likely susceptible. And then Professor Bray and Sancho, also at University of Berkeley, suggested a sort of a modified form. I quite like this one. It's rather simple. It's PI against the ratio of water content to liquid limit, and you can see that the susceptible region is again a PI of less than 12, and when the water content is greater than 85% of the liquid limit, those are likely to be more susceptible. Now when it comes to the CPT, you know, we're used to using soil behavior type charts, and these are actually a little different than classification based on things like Atterberg limits. Remember, the soil behavior type charts are based on the behavior, the in situ behavior of the soil, as opposed to classification on remolded samples. So the in situ behavior is controlled by strength, stiffness, and compressibility. And so you can see here that we know that sand-like soils tend to have higher tip resistance and lower friction ratios, and clay-like soils tend to have lower tip resistance and higher friction ratio. And sort of course, there's a transition zone of mixed soils in the middle. And so in the past we've talked about using this soil behavior type index, IC. So this is an index of soil behavior that combines both the normalized cone resistance and the normalized friction ratio into a single parameter that gives you some idea of where you are on the chart. And so if the soil behavior type index IC is small, you're up in the sandy region, the sand-like soils, and as IC gets larger, you progressively move down the chart and eventually come into this clay-like region. And I had suggested that the boundary between approximately sand-like to clay-like had a soil behavior type index IC of about 2.6. That's this line in the middle. But clearly there's a transition zone, you know, just like as we said, the transitioning from a more sand-like to a more clay-like behavior doesn't abruptly occur at one criteria, so there's a little bit of a transition from one to the other. And with CPT data, that transition also coincides with essentially a drainage transition where sand-like soils tend to be drained and clay-like soils tend to be undrained, and so this transition zone also represents a transition from drained to undrained loading. So we talked about normalized data there, and originally the simple normalization for soil behavior type was this linear normalization, which is the net cone resistance divided by the vertical effective stress. But we now know that when you apply that to a wide range of soils, the normalization is a little bit more complex, and so you essentially have this dimensionless net cone resistance, which is the net cone resistance divided by atmospheric pressure to make it dimensionless, and then multiplied by a stress normalization factor, which is atmospheric pressure divided by vertical effective stress to some stress exponent n. And you know, in the SPT world, that was often referred to as Cn, which is this correction factor for normalization. People used to think it was correction factor for SPT n value, but it's a normalization correction factor. And so n is variable, and in simple terms, when n is 1, it comes back to the simple form that we see above for clay. And we know that for sands, n is often less than 1, and nominally around 0.5 is the traditional number. But you'll see in a moment that recently people have realized that n is probably a variable depending on soil type, density, and stress level. Now originally when I first came up with this, I had suggested the term QC1N And that gets a little bit complicated with all of these subscripts. So in recent years, I've suggested we stick to the uppercase form, where we put uppercase Q and we write QT because ideally it's corrected for unequal end area effects. Now, to be fair, the unequal end area effects of water in sands is very small, so there's very little difference between QC and QT, so it's somewhat of a detail, but it's an important one when you want to extrapolate to a wide range of soils. So now I tend to prefer that we use the term QT subscript, sorry, Q subscript TN, T meaning it's being corrected for water effects to total stress, and then N meaning it's normalized. So sort of dropping that old form of QC1N and going with the new form of uppercase Q. So here's a comparison of the normalization. So the black lines are the ones that I suggested for some time, which is where the stress exponent N is a function of the soil behavior type IC. So when you're in the clay region, stress exponent is 1, and then as you progress up into the sand region, it tends towards 0.5, a lower number. So you can see as it varies this way. And then more recently, I had sort of updated that and included a stress component where it said also with increasing confining pressure, there was a tendency for it to head towards 1. So this contour of 1 tends to move up the chart with increasing overburden pressure. Now notice we're using vertical effective stress, but most people recognize that ideally it should be either horizontal or mean effective stress, but the reason we use vertical effective stress is because typically we don't know what the horizontal effective stress is, so we stick with the one we do know. But it's important to remember that it is influenced by the K0 in the ground, and so you'll see later that we sort of get away with this for liquefaction, since most of the soils that we look at are relatively young, essentially normally to lightly overconsolidated, so K0 tends to be in the range of about 0.5 to 0.6, and so we can sort of get away with using vertical effective stress, even though we really should be using either mean effective stress or horizontal effective stress. We'll come back to that point later to sort of reinforce, to remind ourselves. It's particularly important in ground improvement where you change the horizontal stresses. Now, just a note here, Bean and Jeffries, who use a state parameter approach, they use a stress exponent of 1 throughout for all soils, and maybe we'll come back to that topic a little bit later. Little note at the bottom, I feel that if the stress normalization is done correctly, there's no need for any further stress level corrections. And in liquefaction, there's often this term K sigma, which is a further correction for high overburden pressure. And you'll see later that because I've embedded that in the stress exponent, I don't think we need that later on. Now on the chart here, I show a set of red lines. Professor Bollinger and Bollinger and Idris have suggested a variable stress exponent, and theirs is based on essentially relative density, where essentially they're saying that the denser the sand is, then the lower the stress exponent, and the looser the sand is, the closer it gets to 1, and that's very logical. And I've drawn them as straight lines because theirs are based only on clean sands, and so I can only draw them as straight lines. But when I see them shown over this limited range that would apply to clean sands, you can see that their values are not much different. You can see that we would get values of 0.5 in these denser sands, and we would get similar values of 0.7 or 0.8 in very loose clean sands or even silty sands. So there's not a lot of difference between the stress exponents between those two methods. And particularly given that the case histories are at relatively shallow depth, where the overburden pressure is approximately close to 1 atmosphere. And of course at 1 atmosphere it makes no difference what the stress exponent is, because the stress normalization factor just becomes 1 at 1 atmosphere. So looking at the way the soil transitions from sand-like to clay-like, when I first proposed using the CPT for liquefaction, in those early days, the SPT approach used fines content to try and make a correction to the cyclic resistance ratio as a function of increasing fines. And so I showed that there was a loose link between fines content and soil behavior type index, and here it's illustrated. This is data from Suzuki. This is a plot from the Idris and Bollinger book. And you can see that there is an approximate relationship that as the fines content increases, IC increases. In other words, as you move down the chart, typically the soils have increasing fines content. And here's this boundary of roughly 2.6, and you can see that you can have a soil that has an IC of approximately 2.6, but it may in fact have 100% fines content, but if the fines are non-plastic, it behaves more sand-like. Or you could have a soil that maybe has 20% fines, but if the fines are made up of very highly plastic clay minerals, then it could behave more clay-like. So back in those early days, I had suggested rather than calling this fines content, when you use soil behavior type, you're estimating really an apparent fines content where you're capturing both the influence of plasticity and fines content. So one of the challenges with sampling and any correlation based only on fines content is, first of all, soil behavior is not controlled solely by fines content. It's influenced by the plasticity as well as the amount of fines. And then also, sampling to get the fines content is quite difficult, because you can see in this photograph that's actually from Professor Bollinger, you can see how often highly variable coarse-grained materials are, where they can be much finer and then rapidly coarser and then much finer. And you see how difficult it is to try and sample to get some representation of fines content. If you are going to sample, you're better to select the sampling depth based on adjacent CPT and then use something like these simple push-in samplers to get a small disturbed sample that's perfectly adequate to determine things like grain size distribution, fines content, and Atterberg limits on the finer grain soils. So the method to evaluate the resistance to seismic loading has evolved mostly out of case histories. And when you look at these case histories, they're mostly young Holocene age deposits. In the early days, predominantly clean sands, although later, increasingly silty sands that have been adjusted to equivalent clean sands, and we'll talk about that in a second. And because they're young, relatively normally consolidated, it's just a reminder that K0 is in the region of around 0.5 to 0.6. Mostly level ground. The data is all corrected to an equivalent magnitude 7.5 earthquake. That's to correct for the duration of the earthquake. And then the depth range is typically quite shallow, from 1 to 15 meters, with 95% of the data less than 10 meters. So most of it's relatively shallow experience. And most of it's based on surface observations of liquefaction, things like sand boils, cracks, and deformation, etc. And that may be why the data is a little bit biased of shallow depth, because, of course, you may in fact have liquefaction at greater depth. It's just that they don't result in sand boils, and so people may not have observed that liquefaction had occurred. But the key thing is, typically, even if liquefaction had occurred at depth, then typically you don't see much surface deformation and damage. So that's important later when we get back to it. And then also it's based on average penetration values. In the early days it was average SPT, now it's average CPT values. And so in summary, the database, if you look at the number of case histories versus depth, you can see that most of them are less than 10 meters, with the average being around 5 or 6 meters. So it's possible that liquefaction may have occurred greater than 15 meters. It's just that we don't see many of those effects. Now, back in '98, at the time of the ENSER workshop, Catherine Wright and I had looked at the available case histories then. So the solid dots represented sites that had liquefied, the open ones that had not liquefied. And so by each one of these data points, you calculated a cyclic stress ratio for that earthquake, got the average normalized cone resistance in the layer that was considered to have liquefied, and then based on those that data, you could draw a dividing line, this triggering line. And then once you've got the dividing line, that becomes a triggering criteria where now for a given normalized cone resistance, you could estimate the cyclic resistance ratio. So sometimes these charts look a bit confusing, where they've got data points based on cyclic stress ratio, but often they say that it's a cyclic resistance ratio curve. And that's because it's the two folded in together. Some important things to take note about this early curve. It was mostly for clean sands, for a magnitude 7.5 earthquake. And just like Professor Harry Seed had done before, I kept on these contours that represented approximately the maximum limiting shear strain that would occur. And so you can see that if you had a loose sand that would liquefy, so if you had a cyclic stress ratio larger than the triggering curve for that penetration resistance, then liquefaction was likely to occur. And if it did occur, deformations were likely to be very large. Whereas once the normalized cone resistance exceeds 100, if you've got a cyclic stress ratio from the earthquake that exceeds the triggering line, so you're up here, liquefaction could be induced, but the deformations are going to be smaller. And that's what we observe in the lab, is if you have a medium dense sand and you cyclically load it, pore pressures will develop. It almost gets to zero effective stress, but actually doesn't exactly get to zero effective stress, so doesn't truly reach zero effective stress, so therefore doesn't truly have zero stiffness and therefore doesn't deform quite as much as the loose sands. And of course, the denser the sand gets, you obviously need larger and larger amount of cyclic loading to trigger this response, but even when you do trigger it, it doesn't reach zero effective stress completely, and so the deformations are much smaller. So that's an important observation to remember, is that the amount of deformation likely to get is a function both of the earthquake but also of the density of the sand. The denser the sand, the less likely it is to deform very much. Now, Rob Moss did his PhD at UC Berkeley in 2003, and he expanded the database. So he added a lot more case histories to what you saw in that previous plot. And then in 2009, I sort of reevaluated Rob Moss's database, looking at some of the case histories in more detail, and particularly looking at the continuous digital data. So I reevaluated some of the average numbers he had picked. I didn't change many, but just a few key ones that I thought I disagreed with the average values, and you'll see why later. I focused on a lot of key sites where the average values were very close to that boundary line. Also, Rob had a number of classes of data, A, B, C, and D. He excluded the D data as being very poor, but he kept in the Class C data, and this Class C data was mostly non-standard or mechanical cone data, a lot of it coming from China, where they used a non-standard Chinese cone. And so I felt that it was not fair to include that data. So I actually removed that data, and it does influence the correlation a little bit. And then also I looked at the continuous digital data to evaluate the selection. And I use software to help do that. And so this is the resulting plot. It's sort of very similar to what Rob Moss got. So now you've got the cyclic stress ratio. Solid dots represent sites that did liquefy, open dots that didn't liquefy. And I've shown a variety of the more recent relationships. The solid one is the one back from '98 that we had suggested that ENSO used. You see that Rob Moss's is very, very similar to it. The Idris and Bollinger one is a little bit lower, and then Yuang et al. From Clemson University, his is a little bit higher. But what you notice is that where most of the data is, we've all got relationships that are essentially very, very similar, because that's where most of the data is. Where we differ is how we extrapolate into the region of denser sands, where the data is very sparse. And so, of course, how you extrapolate into that region of sparse data becomes more subjective. These green dots up above, Professor Moss did include some data from China, and that was mostly that Class C data. And he did go back to China and use modern Western standard cones to recollect data from these Chinese, mostly from the Changsheng earthquake. So these green dots represent that newer data that he subsequently added. And you can see it was a larger earthquake. So it does add some data out in this region that's important. But one of the things that comes across is you can see when the normalized cone resistance is greater than 100, then we have very limited data, so it's more subjective on the relationship. But one of the things that you'll see later is this is in the region where volumetric and shear strains tend to be much smaller, and so those deformations tend to be less sensitive to the actual factor of safety you calculate in this region. So that was the relationship at the blow count, and then after the cone resistance popular. And how it evolved, looking at that same data, the one on the left is the open ones that didn't, over, it's a curve over. And so that's how this, so you get these contours of clean sand, different soils. So you may have a clean sand that from the plots further down, but they both have the same clean loading. That's an important concept, that soils with values will have the same resistance about. We chose resistance clean sand correction factor, and this correction factor is simply a function from these contours. Correction evolved. The sand, you know, here's the sites that had silty sands have been shifted over to this clean sand equivalent. So I've illustrated the left, and then it gets shifted to the right to get your curve that applies to clean sand equivalent. Stress ratio for an equivalent magnitude 7.5 earthquake, and so you've got this simplified form. There's just this modifies your given design earthquake to an equivalent 7.5 earthquake. So that's going to last longer. Then the magnitude scaling factor will sort of boot the equivalent cyclic stress ratio for a 7.5 earthquake. Then calculate the clean sand equivalent and then determine the cyclic resistance, the factor of safety. And that's the cyclic resistance ratio to have magnitude earthquakes. And you can file a factor of safety with depth. 1996-97, some researchers went away and sort of wanted to sort of update and modify the method, and CPT method, and Rob Moss looked at the CPT one and then stated the SPT and CPT. So there's some conflict in the original NCR method, which used the Robertson and Wright CPT L, CPT1, and then the Idris and Bollinger CPT method. So what happened at the cyclic stress ratio from the case histories? The dots moved, of course, the trigger line moved, and so therefore the calculation of safety, the factor of safety didn't change very much because both of them changed by essentially equal proportions, and so there wasn't much change in the factor of safety for the given method. So if you're going to use like the NCR method, ideally you should use this ratio and the same component for cyclic mix and match. You can't use the Idris and Bollinger method to get cyclic ratio because they're not a match pair. Which is where the risk that there's probably a lot more sites that just a little bit. And then, of course, the biggest thing was by simple things like where did they assume the water total overburden pressure, in other words, what unit weight did they assume, and then, more importantly, how was quite a controversial issue about which is the right way to do it, and move the data points around and use slightly different stress reduction factors, K sigma, Bay sigma if you use the corrections to clean sand equivalent, the data, and then you see the way the relations, and Crester has suggested one, and that was pretty aggressive. That was maybe a little bit too aggressive. Suzuki had a relationship on the cases, and Rob Moss even more gentler. So you see the comparison. Bollinger, because theirs is based strictly on fines content, so correction over to an equivalent soil behavior type. Similar contours, and I've shown here the zone that represents where most of the data is, and so where most of the cases, of course, when you get outside that data, that the corrections start to change quite a bit. What you'll see later is often when you compare the methods in the historical case history data, then you often get very similar results, but when you the results can start to differ, and we were all using essentially the same case history database. So I'm going to show a site that's right on the boundary curve. This is in the Imperial Valley in Southern California. 6 CPTs carried out, and it's a silty sand to this boundary IC of 2.6. You notice I've shown a rather large dot here, and that's because, of course, not just a single value. It's actually a range of values of which people try to choose. It suffered a series of earthquakes. Valley earthquake, which was about a meant to be considered about 0.13 G, was considered to be a fraction. So there were no sand boils, no damage. And then just 2 years later, we had the Westmoreland earthquake. Bigger in surface acceleration. It was a little bit larger, 0.09 to 0.1. Those were observed. Some surface movement was observed. So just for it, and it's mostly a silty sand. So there's a relatively large correction for methods. And so if you look at the data, here's we're closer to the chart, and so you can see that the no liquefaction one's plot. And so when you compare the 3 different methods, so this is the estimated, so the lower the factor of safety, the bigger the volume. Compare the method, the Robertson and Wright method that NCR recommended, essentially said there would be no liquefaction, less than half a centimeter, so barely noticeable. The Idris and Bollinger shows higher, on average, closer, a little bit less than 1 centimeter, and then the Moss et al. Method, giving a much higher, where no liquefaction was observed. So you can see, obviously, I have this between mine and Idris and Bollinger. Idris and Bollinger may be a little bit more conservative on this one, and the methods they do calculate a little bit different. But in terms of factor of safety, in general, they're within the margin of uncertainty based on data scatter, local variations, unit weight, groundwater level, estimates of seismicity, exactly how big was the surface acceleration, etc. So there's a lot of uncertainty when you compare the methods. Back in '98 was deterministic, but Yang and his colleagues at Clemson University did look at the database and did a probabilistic analysis, and what of liquefaction can be expressed by this very simple formula that's controlled by the factor of safety. Faction is about 35%. So it's slightly some level of concern. So with sands and silty sands, but when you move into clays, in many respects, clays are actually very similar to normally or lightly over-consolidated clays. Loose sands are normally consolidated clays, both pore pressures, whereas dense sands are somewhat similar to over-consolidated clays, just as over-consolidated clays will do. but parameter, whereas in clays we tend to think in terms of stress history or OCR. And so researchers, Idris and Bollinger being some of them, has suggested that you could estimate the cyclic stress ratio exceeded about 80% of the undrained strength. This makes sense because the cyclic stress ratio is essentially the undrained strength is the shear strength divided by vertical effect. Earthquake is going to load the soil close to some level of deformation, hence that sort of 80% factor. Static shear stresses, recognizing that the foundations are already loading applied to the clay. So part of the unstatic loading, then if you come along and cite loading that it can take before it starts to soften, the cyclic stress ratio is a function of this K alpha is in the range of 0.8 to 0.4, 0.5, and so a significant influence on loading the earthquake. Cyclic softening or deformation is always where the OCR is less than about 4, or tend to be dilatant. You can estimate that directly from the CPT. Contours that were based on case histories predominantly on sandy soils. In clays, the cyclic resistance ratio is controlled by OCR, which is controlled purely by. So in 2009, I had suggested that you actually can S-shaped curve, almost like a number 2 behavior, without the need of a cutoff, because prior to said when soils have a soil behavior type IC less than 2.6 liquefaction, and when IC was greater than 2.6, they were likely susceptible to cyclic softening. And so here it sort of goes beyond that. I went back through the database, that same database didn't occur in the sandy layers. You could look at the clay layers, not soften. And so that's what these open squares are. They're the case histories that have included the clip. Fits very well with this horizontal line based on famous sites where softening did occur. This was in Turkey, large 3- and 4-story buildings, and then for the smaller mud fits, San Francisco, Young Bay Mud, Adu. And there's some signs of deformation from slope. So using this updated method, you can actually, so you can estimate both sound-like. Reminder that one of the nice things about seismic CPT is you can small strain stiffness. And there are methods of wave velocity. And here's an published in ASCE. And so it added more case history data, a lot more data. And they red line through their probability of about 20 to 30%. So you can see where the boundary line comes. And essentially observed whenever the normalized shear wave velocity to be sure of it. Once you get greater than 2 shear wave velocity, is that it's measured at 1 meter intervals, so it's a more subdued. Where most of the liquefaction occurs, it's all between shear wave velocities. Measure the shear wave velocity very accurately to try and use this method. And also, shear wave velocity is quite sensitive to things like aging and cementation. So, for example, you may be cemented, so the light level of cementation, but if you hit it with a that will break the cementation at a seismic CPT. So what are the consequences by reconsolidation of the soil if soil gets ejected, sandbars, etc., or localized shearing and to try and estimate post-earthquake settlements? Lateral spreads due to shear stresses. So as the deformations to where the static shear stress is likely to be, and that's why you get lateral spreading in part 2. So the fact a lot of them, and they're quite complex. There's, of course, the soil, the age, degree of saturation, cementation in the depositional environment, etc. Baking frequency, content of motions, exactive topography, the geometry of the site, the metric profile. It may not be truly hydrous, water drain away, etc. And then, of course, 3-dimensional facts, ground cracking, low permeable, the final deformation. So methods that have evolved have had to try and simplify deformations in sandy soils. You know, it's pretty difficult under seismic loading. It's difficult under because they're approximate at best. So, but for low to moderate risk projects, you need a factor of safety for liquefaction. So, and most of them are linked to clean sand equivalents. I want to think about doing more complex new indicates need. So, a couple of methods, CPT-based methods. So, I had a graduate student called Robertson, and we wrote a couple of papers. The one in 2000, they were both based on the extensive lab data from Ishihara and Yosemite, metric strains for clean sands, and it uses the clean sand histories. So, here's a sort of the famous summary, a range of soils in multi-directional loading, and eventually came up with this nice relationship that shows factor of safety against post-liquefaction volumetric strains, and then also with nice about this is you can see that even when the factor of safety is slightly larger than 1, you can still safety is greater than 1. Pore pressures did develop large, but there will be some post-earthquake deformation. You can see that vol strains are less than 3%, and then once you get to a factor of safety of up around 2, it all goes to 0. But what it also shows is if your deformations become very large, volumetric strains, rapidly go up to about 5% and then 20%. But you see that for denser soils, so normalized cone resistance of around 100, here's factor of safety gets less than 1. You see that volumetric strains are less sensitive to what the factor of safety is. And the shear strains are shear strains. So the Zhang good results for the Marina District and Treasure Island. It also showed the importance of thin layers and transitors, 3-dimensional factors, proximity to results in Taiwan. So here's some of the challenges. So that liquefies is at great depth. You may calculate a certain amount of volumetric as much damage if it's very deep. And so there are a number of methods that try to in part 3. is much closer to the footings, then damage is likely to be much more of vertical settlement. If the footings are very close, they get ejected sand, etc. So the differential settlements of the building is much closer to the footing. Of course, if you've got multiple layers, the top one may not, but since cyclic shear liquefies first, and you can still get liquefaction of the lower layers. A very heterogeneous soil deposit that liquefies it. Now for lateral spreads, I mentioned if you've got level ground with the soil liquefies, then it tends to ratchet towards the free face. You get larger deformations closer to the free face. There was a nice paper in ASC in 2006 by Taiwan earthquake, some case histories, that if the layer that liquefied was the depth of the deposit is from the upper surface, then it should be lateral. Now I just want to tell before in the interpretation of CPT, so if you're going from say a transition up to its correct value, so the continuous data is core transition zone. And in interlayer excessive conservatism of overpry, assuming that all of these little thin zones in the transition contribute to the deformation which they provide. Software packages like Slick, which will identify these transition zones and removing them to show examples with the software. So Moss Landing is a good example. This is actually the example that UC14, which is at State Beach, 5%. Soil behavior type IC is quite small at 1.6. And then way at Moss Landing, the percent IC about 2.2. So interesting, if you look at the land region and they both plot on the same clean sand equivalent. So although they've got different similar resistance to cyclic loading. So you can see UC8 was correction, but they end up essentially at the same location. Here's the spring down to the harbor at Moss Landing, and you see for 6 or 7 meters overlaying CPT profile. 8.3 meters, and then there's a climb back into this sort of silty. It is relatively free, 2 meters down to raining, relative Robertson ride method. Here's the cyclic resistance, and you see liquefaction predicted from the water table. Liquefaction a little bit deeper, but you can see in terms of deformation sand, both for vertical sections, they varied. The deformations were influenced by the fact that they wanted meters of for 80, it says centimeters, an assumed free face height objective because it's not exactly level decision on exactly what to use. I'll talk about this as a parameter that Iwasaki in Japan came up with, and it's a way of weighting the damage as the factor of safety, and you multiply it by a weighting factor that is 1, so it weights it more near the surface, and then you see likely you're going to see damage. You see it's Robertson ride method. Here, very similar results. Very similar results. There are difference, particular difference between the deformation. Then an equivalent SPT method, and then the Berkeley group interest in Bollinger an SPT approach. And this is just a picture which had a borehole next to it, showing, of course, the SPT has less detail because so you don't get the same level. CPT came from the Marine Lab, where a large CPT from UC8, a little bit of sands and clays, and a bit of a sand layer, little clay. 7.5 meters down to 10 to have liquefied. You see IC is large. Negative of hydrostatic pressures are, so again, it does predict liquefaction in that silty predicted to occur, and that's where they were. At Moss Landing, there was a nice example at the Marine. This was UC14, and here they had a slope indications after the earthquake compared to the CPT-based NCR. There was a point from Moss Landing that I showed on these. So one of the challenges for nice figure out of Idris and Bollinger's book where they show a building, and if you had like 8 lateral spread, then you're going to get a lateral spread that will influence the building. If only a few of them, you might get an isolated movement. Of course, if there's one at the back, it's unlikely you're going to get movement if it's required to try and estimate the complexity. So to summarize, a risk-based approach is a useful way to determine the level of calculation analysis. On deformations is a characterization, usually in a pretty cost-effective way. You can get soil samples, so if you need to verify the clay-like or sand-like behavior, and in fact NCR recommended that whenever IC exceeded about 2.4, then it was recommended to take samples and to verify whether or not the soil was going to be more sand-like or more clay-like, based primarily on Atterberg limits and grain size. So again, summarizing, CPT provides a fast estimate of the potential for cyclic liquefaction and softening via the cyclic resistance ratio. You can estimate post-earthquake settlements and lateral displacements, although it's clearly an estimate. The real deformations are controlled by many variables. And you can screen for flow liquefaction, and that's what we're going to cover in part 2. And recent updates, I talked about stress normalization, and recently I sort of updated it that included a stress component. Also extending it into clay-like regions so you wouldn't actually have to have a strict cutoff of IC. And what you'll see when I demonstrate in part 3 with the software, what you can do is you can run the method two ways. You can run it where you're only looking at sands and you estimate a cutoff, typically at about 2.6, see what the result is, and then click all soils, the updated method, and see how much it's influenced by the clay layers. And then, of course, the importance of identifying transition layers, particularly in interbedded soils where there are a lot of transition zones, and if you don't remove them, you'll be excessively conservative. Of course, if you keep them in, then you will get a conservative estimate of deformation. And, of course, concluding that Seismic CPT provides the added benefit of giving you two independent measurements, both the shear wave velocity and the cone data, to do an independent evaluation. But the cautionary note is that shear wave velocity is more sensitive to things like cementation and aging, and so you have to be careful for seismic loading to make sure that it's not just lightly cemented, and the risk is that cementation could get broken. So that was somewhat of a rapid overview, an introduction to CPT-based evaluation of liquefaction. In part 2, we'll cover static liquefaction, and then in part 3, we'll look at worked examples using software, and by doing that, we'll look at some of these issues again by looking at real data and examples. So the next two will follow on from here. So Kelly's written many questions out, so obviously I triggered quite a few questions. So let's go through some of them. So the first one, any recent advances made for liquefaction analysis of silts based on CPT since Robertson arrived? Well, essentially silts are a fine-grained soil, and the key is, are they going to behave more sand-like or more clay-like? And what we do know is, although silt soils do behave more in a more sand-like response because they're typically low plasticity, so they're more sand-like, but they can often plot a long way down the chart. So they often plot, if they're normally consolidated loose silts, then they quite often will plot in the clay-like region, saying that they look like they're behaving like clays. And interesting enough, if you estimate the cyclic resistance ratio based on their undrained strength ratio, in other words, as if it was a clay-like material, then you often get very good answers compared to high-quality lab data. So the progression since '98 is that, yes, you can interpret silts using CPT data, and you can use that updated version that sort of extends the method into the clay-like region. Even though they're silts and they tend to fall in that clay-like region, they still tend to get the prediction right, because if they're loose, normally consolidated, they're going to plot low down on the chart, so they're going to have a low undrained strength ratio, so you're going to predict cyclic softening. The real question comes is, how well can you estimate the amount of deformation afterwards? And that's where we still need quite a bit of research, is how much do these non-plastic or low plastic silts deform after they've been triggered to liquefy from an earthquake. And in general, I think that's where treating them as more sand-like tends to be conservative, is that if you treat them as sand-like materials and use the clean sand equivalent, then you do predict pretty large volumetric and shear strains, which probably are generally somewhat conservative. So more research needs to be done to sort of verify how exactly we should handle those materials. Next question sort of evolves out of California, where it talks about SB 117, which is a guide here in California. It currently indicates that if PI is greater than 18, soil sensitivity should be evaluated. Are you aware of any sensitive clays in California? And the answer is, fortunately, California doesn't have a lot of sensitive clay. In the Bay Area, the young Bay mud actually is quite sensitive. And so if you're in the Bay Area and you're dealing with those young, essentially normally to lightly over-consolidated young clays, then, sorry, I put down my microphone. I was so focused on the questions. So are there sensitive clays in California? The answer is yes. Not highly sensitive, but we do know that up in the Bay Area, these young bay muds that are essentially normally to lightly over-consolidated clays of moderate PI are quite sensitive, and I think that there is a strong likelihood that they will suffer cyclic softening in a very large earthquake. And so that's an area that I'm encouraging our colleagues at Berkeley to consider is to re-look at the young bay muds and possibly install slope indicators around the bay area so that if a larger earthquake occurs, we actually can see how much deformation occurs in these normally consolidated clays. So next question is actually quite a common question, is opinion on liquefaction beyond 15 meters in depth. Can you use the simplified method to liquefy, to evaluate liquefaction beyond 15 meters or 50 feet? And the answer is yes, you can. The method does tend to be conservative, though, because it does tend to predict liquefaction at greater depth. I think the real issue comes is not whether or not it will liquefy, but whether, what the likely consequences of any liquefaction will be. And so the method, it's not uncommon to predict that layers, down 20, 25 meters appear that they could liquefy. The issue is, what will the deformation be? Now, if you have buildings on shallow foundations, it's likely that the damage potential will be relatively small. Even though you're calculating that these deeper layers will liquefy, the deformations are likely to be small. And there's a growing consensus of following trends like the approach by Iwasaki, where you weight things as a function of depth. And Setin had a paper, it was an SPT approach, but essentially he included a weighting factor, and he actually went to 18 meters. But a weighting factor that weighted the volumetric and shear strains as a function of depth. So although you might calculate volumetric strains down at 20 meters, you're going to weight them essentially at 0, and so you're not going to include that in any surface deformations. Now that's assuming the building's on shallow foundations. Now of course if you have a building on piles and the piles extend down into this region of liquefaction, then I think you need to evaluate what the effect of some softening of the soil around the piles at greater depth would have. Now typically if it's just a small zone, then the pile is not going to fail per se, but the pile may experience slightly larger settlement or deformation due to liquefaction of some of the layers around the pile. So I think again you have to use your judgment in terms of what you think the consequences of liquefaction might be, and particularly as it goes deeper, the issue of whether or not it's going to influence. Now, of course, with large dams, the issue tends to be is whether or not liquefaction will trigger strain softening, and that's an issue we're going to cover in the next webinar in 2 weeks' time when we talk about flow liquefaction or static liquefaction, which is a strain softening response, and so that's a separate topic, which is also an issue of will it occur at great depth. So next question, mentioned calcs where for level ground, less than 5% slope. What do you do if you have a steeper slope? So yes, although the simplified approach was designed for level ground or gently sloping ground, people clearly are applying it to more steeply sloping ground. And the issue, and we'll cover it in the next part, the issue really there is that is there a risk of triggering static liquefaction? In other words, is there a risk of triggering strain softening response in steeper ground that could in fact trigger a flow slide? And so you may in fact have seismic liquefaction that could induce some both vertical and lateral deformations, but what you don't want is you don't want to trigger significant strain softening that would trigger instability in a major slide. And so we're going to cover that in part 2 in a little bit more detail. So hopefully I'll come back and answer that a little bit more clearly in our next one. So it says, how do you calculate the value of AMAX for a design earthquake? Now that's a good question. It's a tricky one because often what happens is if you've got a site, you ideally do a seismicity analysis to try and get a handle on what the design earthquake will be at that site. And in simple terms, you can go to, here in the States, you can go to USGS maps that will show you what the peak acceleration is in rock at roughly that location and the magnitude of the earthquake. And then you have to make an estimate of how much that acceleration could get amplified as you come up through the soil. And in simple terms, the deeper the deposit of soft soils, the more likely you're going to get amplification. And then there are correlations, simple curves that give you a guidance on that amplification. Now you can either just use those curves to estimate the amplification, or you can do a one-dimensional sort of shake type analysis to bring up the rock shaking up through the soil profile and then get a better estimate of what you think the maximum acceleration at the surface will be for your design earthquake. And that's controlled a lot by the shear wave velocity profile. So again, Seismic CPT is nice because you get the shear wave velocity profile, and that can guide you on how to do that one-dimensional analysis to estimate that amplification. So comment on the iterative circular nature of the normalized cone resistance and IC calculation with respect to the dependence on the exponent n. Now we covered this in one of our previous webinars, and the issue is how do you calculate this normalized cone resistance given that it's got a variable stress exponent that depends on IC. And so the way it's normally done is you typically start off by assuming that n is equal to 1, and then you calculate the normalized cone resistance and then calculate IC, and then based on that IC go back in, recalculate the stress exponent n because it's a function of IC, and then recalculate the normalized cone resistance, and you iterate. And you typically only have to iterate 2 or 3 times, and very quickly it homes in on the right answer. And so it's a very simple procedure. Most software programs do it very quickly, and it's relatively easy to even program that on the spreadsheet to do. So it says factor of safety between methods falls plus or minus 30%. Why does settlement prediction have such a large difference? Well, that's a good question. And I think that's because each of the methods estimate settlement differently. And to be fair, the Moss et al. Method, they only went as far as estimating factor of safety. And so to estimate settlement, we then had to use the Zhang et al. Methods based on that factor of safety. But you notice that when the material is quite loose, the amount of volumetric strain and shear strain is very sensitive to how big the factor of safety is, how loose the soil is. And so since the methods normalize the data slightly differently, so they're sort of essentially getting slightly different normalized cone resistance and therefore slightly different estimates of how dense the soil is. And then, of course, slightly different factors of safety. If the soil is loose, it's very sensitive to volumetric strains. Now, if the soil is quite dense, it's relatively insensitive. So, that's a good point, is that although the factor of safety may not vary an enormous amount, the deformations can vary a larger amount, particularly for looser deposits. And so you'll see when I demonstrate the software package I use, Slick, allows you to compare the different methods. So with just a click of a button, you can do a very quick comparison to see how sensitive your site is to the different methods. Next question, what method do you recommend for liquefaction based on shear wave velocity? Well, Anderson Stokey published their method. It was in the Yao et al. One in 2001 in the NCS summary paper of 2001. And then, as I said, just this year, just last month, Kenyon at the USGS with some colleagues updated that relationship where they went to a lot more sites, collected a lot more sites. And so if I just flip back to it, so I would recommend using the updated version. And I think the trend is definitely to move the curve over a little bit. Andrus, their relationship is essentially maxed out at close to 200 meters per second. Now you can see it's moved over a little bit to about 230 to 240. So it's creeping a little bit to the right at the upper region. So this one by Kayan et al. In 2013 is the one. Sorry, I mispronounced that. Thoughts on difference between shear wave velocity and CPT and PS logging for shear wave velocity? Okay, I've already mentioned that if you do CPT and shear wave velocity, if the two methods give the same results, there's a certain comfort level. It's probably a young, uncemented soil, and therefore the correlations are working quite well, and the two methods give similar results. If they give different results, then that's often a warning that something unusual is about the soil. Maybe either the soil is interbedded and the shear wave velocity is unable to pick up the level of interbedding, or that the soil might be lightly cemented and the shear wave velocity is giving a higher small strain stiffness, and therefore predicted that it may not liquefy because of that slight cementation. And you have to judge whether or not the earthquake is big enough to break that cementation. Now, in relation to PS logging, seismic CPT is very good down to 30, 40, 50 meters. As you go deeper, it becomes harder and less accurate. But PS logging is the other way around. PS logging tends to be a little bit more difficult to do at shallow depth because the logging tool itself is quite long and requires a mud-filled or water-filled borehole. And so the PS logging tends to work really well in very deep boreholes. So the two become very complementary. Seismic CPT for relatively shallow depths, PS logging for very deep boreholes. And so since liquefaction tends to be limited in the upper 15 meters, then seismic CPT tends to be the preferred way to go because it's mostly at shallow depth. Thoughts on vibrocone to study liquefaction potential? Well, a number of people have looked at it. The Japanese have looked at it. Professor Main have looked at it. He's looking at putting a little vibrator in the cone so that you push it statically, get the cone data, and then move over, push it again with the vibrator turned on where you're hopefully inducing some liquefaction and see how the cone data is reduced due to that vibration inside the cone. It hasn't worked out very well. It shows promise, but it's very difficult to quantify, and part of it is, again, whenever you have some sort of dynamic feature within a test, it's hard to standardize the level of vibration to make sure that the level of energy being imparted to the soil is consistent. And that seems to be the biggest challenge, is controlling and standardizing the level of energy imparted to the ground. And so I think that's why the vibrocone has been a bit slow to gain acceptance, and the fact that you have to do 2 soundings, etc. Next question is, how can you use the CPT to estimate loss of effective stress around piled foundations during earthquakes? Okay, good question. So if the piles are already installed, because if it's a driven pile, you're going to densify the soil around the pile. So the soil close to the pile is going to be denser than the soil further away. So if you do a CPT, if you do it a long way away, then it's not truly going to capture the soil close to the pile. So you can see how difficult this could be. Obviously, if you push a cone some distance away from the pile, you can estimate whether or not you think the soil is going to liquefy. And of course, if the factor of safety is less than 1, it's essentially saying that you're going to get close to 0 effective stress during the earthquake. And you could assume that that was occurring close to the pile, and you could try and estimate what influence that would have on the pile. Essentially what you could do is, in very simple terms, you could look at the resistance along the length of the pile, and in the layers where you think liquefaction is going to occur, you could drop that resistance to 0 and then see how much the pile would deform. It's not going to necessarily fail, it's just going to deform a little bit more. So it affects the load deformation response of the pile. Now, as I said, if it's a driven pile, life's more complicated because you've densified the sand around the pile. And so if you're doing the CPT 1 or 2 meters away, that's telling you what the soil is 1 or 2 meters away. It's not telling you what the soil is right adjacent to the pile. And so although you might be predicting liquefaction a couple of meters away from the pile, it may not actually liquefy immediately adjacent to the pile, and therefore, of course, the pile may not be affected by the earthquake. And that's consistent with a lot of case histories. People have observed that in driven piles, most foundations on driven piles perform quite well during an earthquake. The only times maybe they don't perform so well is when you get large lateral spreads that could break the piles. But even in cases in the Gata where buildings, 20 years later were excavated down, they excavated the piles and saw that all the piles were broken due to a large lateral spread, but yet the building performed perfectly well. So clearly it's quite a complex soil structure interaction, and there's no simple solution. Next question, can you say if liquefaction potential calculations, shear wave velocity are more or less reliable than the CPT? There are uncertainties in both, correct? Yes, so that's true. The advantage of the CPT, it's continuous. You get continuous profiles, very reliable measurements. The downside is that when you encounter silty sands, you have to make these relatively large corrections due to the increased compressibility due to the fines content of the silt. Whereas shear wave velocity, you don't need to make these corrections. Essentially, there's almost no correction for fines content with shear wave velocity, but you don't get such a continuous measurement. It's a more subdued averaging measurement, and you're more likely to miss, a slightly stiffer and slightly softer layers. So with the shear wave velocity, you may in fact miss some of the weaker, softer layers that the CPT would pick up. So of course, the two together become very complementary. The CPT gives you that continuous profile where the shear wave velocity, you don't have to make big corrections for voids content. So Seismic CPT is a nice thing to do. You get the two together. If the two give very similar results, then you feel very comforted that the ground conditions are essentially well behaved. One of the last questions, do you recommend increasing the cyclic resistance for Pleistocene sands? In other words, do I recommend an aging factor? And that's a good question, and the answer is yes. The difficulty is to know how big that is. But Professor Andrus at Clemson University, he's doing some nice work recently where he's suggesting you measure the shear wave velocity, because shear wave velocity is quite sensitive to aging, and showing that if the measured shear wave velocity is larger than what you would have estimated for a Holocene age uncemented sand, then you can use that increase in shear wave velocity as a measure of the aging, and therefore as a measure of the aging factor that you would multiply the cyclic resistance ratio. And you'll notice that when I show you the software in part 3, that there is a little feature in the software that allows you to put in an aging factor to correct for that. The challenge is how to actually get that aging correction factor, and Andrus, I think, is on the right path where he's suggesting using the shear wave velocity as a way to do that. One of the dilemmas is, if the soil is cemented, so you can get this apparent aging by light cementation, you have to be a little bit cautious about separating the effect between bonding and aging. And we can maybe discuss that more in a subsequent webinar. One of the questions, in a marine environment, is it customary to assume that no liquefaction deeper than 20 meters below seafloor? That's a tricky one, and I think really it's a function again of geometry and consequences. If you've got essentially level ground conditions, then just like onshore, sure you might predict that liquefaction might occur at greater depth, but it's not going to cause any damage. And so again, if you've got essentially level ground, not much consequence. The difficulty comes if you've got sloping ground, or if you've got a significant drop-off in the seafloor, and so you've got a steep slope nearby, and the risk, again, of strain softening response, where the earthquake could in fact trigger strain softening and therefore flow slide. And that's what we're going to cover next week on that issue of flow or static liquefaction. So one of the next questions about marine sites, is there a minimum residual strength for sand to evaluate lateral capacity of piles? We'll sort of cover that next week when we talk about strain softening, because when we talk about residual strength, we're really talking about strain softening response, and I'll try to cover that in 2 weeks' time in our next one. So estimating deformations for cyclic softening of clay-like soils. And yes, I didn't touch on it here, but in the publication that the presentation I did in 2009 in Tokyo, where the sort of updated method was published, I did talk about that clay-like soils tend to have smaller volumetric and shear strains, and how you might estimate that. And so I didn't cover it here. I'll try and include that in our part 3. Try to remember to include that. But essentially, there's a way of saying that the more over-consolidated the clay is, then the smaller the volumetric and shear strains are going to be, and there's a sort of an automatic way of estimating that. And in the software, I tend to recommend a sort of a default value where don't let the volumetric strains and shear strains get too large, because experience shows that the more clay-like the behavior, then the smaller those values are. I can touch upon that a bit later. Okay, I think that about concludes it. I'm sure some people are hanging in there. We're over an hour and a half now. Just make one last plug. Kelly has reminded me to remind people about that we're organizing the 3rd symposium on CPT in 2014 in Vegas. So CPT 14, that's basically a year from now. And so we're still accepting abstracts. So if anyone's got any interesting projects that they're working on that they want to write up in a short paper, then feel free to submit an abstract to that. So that concludes this webinar on part 1 of evaluating soil liquefaction from the CPT, and we'll go into it some more in part 2, which would be static and flow liquefaction, and then part 3 where we'll look at worked examples and maybe be able to cover some of these questions by actually looking at the examples and how we look at real data. So thank you for attending, and if you want to go over this again, of course it will be recorded and you can watch and listen at your leisure. Thank you.